Welcome back everyone to 6.3, the natural exponential function. In this video we're going to be dealing with the calculus of natural exponential functions, that is e to the x. So let's get it going with a remark. So the natural exponential function has a remarkable property, mainly that it is its own derivative, that is dx of e to the x is equal to e to the x. So in general, if we combine this with the chain rule, right, derivative of the outside, leave the inside alone, times the derivative of the inside, du dx. So let's try to apply this to this following example, right? So if I want to take this derivative, well, the first thing is I take the derivative of e, which is itself, and you leave the inside alone. So that's going to be e to the sine of 3x, leave that alone, times the derivative of the inside. Well, the derivative of the inside, well, the derivative of sine is cosine. And you can see there's another chain rule, right? You leave that inside alone, and then you times the derivative of its inside. That's 3. And so, if we rearrange this a little bit, 3 cosine 3 of x, e to the sine of 3x. And that would be my final answer. Another note, since it's its own derivative, well, that means if you integrate e to the x, you get itself, right? Because the antiderivative of e to the x would have to be e to the x. Of course, if we're doing a general antiderivative, then you have this plus c. All right, so let's try to do a little bit more difficult question. Find the equation of the tangent line of this curve at a specific point. Ooh, tangent line, it's been a while, right? So we have a specific point that we want to attach the derivative to. So let's remind ourselves the equation of the tangent line is y minus f of a is equal to the slope, f prime of a, times x minus a. And we have to wonder, what is a, what is f of a? Well, a is just the x value, and f of a is the y value of the function at -2 in this case. So, according to our tangent line equation, we have y minus, now f of a is e squared, and then a is -2, so this is going to be x plus 2, and now we need to figure out what is that derivative of f at -2. So that means we need to figure out the derivative of this equation. And well, this looks like I'm going to use the quotient rule here. So the quotient rule. So let's see, f prime, that's going to be the derivative of the top. Well, the derivative of the top is going to be, well, 4 is along for the ride. It's a nice constant. And the derivative of e to the negative x is e to the negative x. And then there's a chain rule, right? Chain rule says I need to multiply by -1. And then times the derivative, sorry, times just the bottom minus the top times the derivative of the bottom. So now I have 2x, all divided by the bottom squared. All right, so that's our quotient rule. And we can simplify this down. In particular, we can notice that there's a negative, a 4, and an e to the negative x in both numerator terms. So let's factor that out. And then I can also see the stuff that's left over, x squared and plus 2x. And in the denominator, I can simplify this. Oops, I forgot. It's x squared squared. Let me go ahead and fix that really quick. It's the bottom squared. I said it, but I didn't write it. So x squared squared, that's going to be the same thing as x to the 4th because of properties of exponentials. And so I need to plug in -2. So f prime at -2, I wonder what that is because that is going to complete my tangent line equation. So if I plug in -2, well, -2 is going to be +2. And then, so -2 squared is 4. And then -2 times 2 is -4. And so, 4 minus 4, that's 0. 0 times anything is 0, so great. This is just 0. Well, now when I plug that in, well, this is kind of a sad tangent line equation now, because 0 times anything is just 0. So that's just going to be y equals e squared. This is my tangent line equation. And it may be fun if you have some graphing software, graph this function, graph y equals e squared, and you can see that it just barely skims. It is the tangent line. It's a nice horizontal tangent line. All right, let's do one more problem, integrate something interesting here, right? So this is going to be a u substitution here, but now I have this crazy function with e to the x's. So I'm going to let u usually is my inside function. So looking at this thing, I think my most inside function is going to be this 3 plus e to the x. So let's try that. In that case, my du is going to be e to the x dx. So if I swap these things out, right, instead of 3 plus e to the x, I'm going to have u. So this is going to be square root of u. And then let's see, instead of my, let's see, 4 I could pull out, right? And then e to the x dx I trade in for du. All right, so now let's integrate this thing. When I integrate u to the 1/2, it becomes 2/3 u to the 3/2. Of course, plus c, it's a definite integral. And then the last step is to go ahead and exchange back, right? My u is this 3 plus e to the x. So let's go ahead and exchange that, simplify a little. And so my final answer is this 8/3 times 3 plus e to the x, all raised to the 3/2 plus c. All right, and that should do it for us here in 6.3, the natural exponential function. Go ahead and get started on your homework, and I'll see you next time in 6.4. See you then.